More than 2,000 years ago, a ship sailed through the waters between the Greek mainland and Crete. It carried a remarkable cargo: fine glassware, bronze statues, coins, luxury goods, and objects from across the eastern Mediterranean. Then something went wrong. The ship went down near the small island of Antikythera. Its cargo disappeared into deep water, where it would remain untouched for almost 2 millennia. In 1900, sponge divers searching the waters around Antikythera found the wreck by accident. They reported statues lying on the seabed. At first, the discovery looked like a familiar archaeological treasure: marble figures, bronze sculptures, pottery, and fragments of a Roman-era shipwreck. Among those finds was an object that did not look important at all. It was a broken mass of bronze and wood, darkened by corrosion and covered in the damage of the sea. At first glance, it could have been mistaken for a piece of the ship itself. But when researchers looked more closely, they saw something impossible to ignore. Inside the corroded metal was a gear. Not a simple wheel. Not a decorative pattern. A precisely made gear wheel, with teeth cut into bronze. That discovery opened one of the strangest mysteries in the history of technology. The object became known as the Antikythera Mechanism, named after the island near which it was found. It was built in the ancient Greek world, probably during the 2nd century before Christ. The ship carrying it sank decades later, in the 1st century before Christ. For centuries, the mechanism rested on the seabed. When it was finally recovered, it was broken into fragments. Much of the original machine had disappeared forever. The wooden case was gone. Many of the dials were lost. Some of the gears had been destroyed by corrosion. And yet, enough survived to reveal something astonishing. The Antikythera Mechanism was a hand-powered astronomical device. By turning a handle, its gears could model cycles in the heavens. It could track the movement of the sun and moon. It could follow calendars. It could predict the timing of eclipses. It could even mark the cycles of major Greek athletic games, including the Olympic Games. It was not a modern computer sent back through time. It was not proof of a lost supercivilization. And it was not magic. It was the work of ancient engineers who combined mathematics, observation, metalworking, and imagination in a way that historians had not expected to find in a surviving object from this period. For a long time, the mechanism seemed to stand alone. No other device from the ancient world had survived in quite the same form. It contained dozens of gears, intricate dials, and tiny inscriptions written in Greek. It was a machine designed to make the order of the cosmos visible. But the greatest mystery was not only how it worked. The greater mystery was this: if ancient engineers could build something like the Antikythera Mechanism more than 2,000 years ago, how much knowledge has been lost since then? And what else might still be waiting beneath the sea? The Antikythera shipwreck was discovered at a time when underwater archaeology barely existed. The sponge divers who found it had no modern diving equipment, no underwater cameras, and no careful archaeological plan. They descended in heavy suits and copper helmets, breathing air supplied through hoses from the surface. At depths of roughly 50 meters, they found a scene frozen in time. Bronze statues lay among rocks. Marble fragments rested beneath sediment. Amphorae and glassware were scattered across the seabed. The ship itself had vanished, leaving only the cargo and the remains of its journey. The recovery operation was dangerous. One diver died, and others were badly injured by decompression sickness. Even so, the finds were brought to the National Archaeological Museum in Athens, where researchers slowly began to understand what they had recovered. For decades, the bronze fragments received little attention. They were difficult to read. Saltwater had transformed them into green and brown lumps. Wooden pieces had almost disappeared. The gears were crushed together, and inscriptions were too faint to understand. But a Greek politician and scholar named Spyridon Stais noticed a gear embedded in one fragment in 1902. It was a small observation with enormous consequences. Ancient Greeks were known for mathematics, astronomy, philosophy, architecture, and mechanical devices. But complex bronze gear systems were not supposed to exist in surviving objects from this era. The mechanism challenged a simple story about history: the idea that technology always develops in a smooth, upward line. History is rarely that neat. Knowledge can be forgotten. Workshops can disappear. Libraries can burn. Skilled craftspeople can die without passing on their methods. A society can lose access to materials, money, institutions, or trade routes. Sometimes an invention survives only in a single object, buried by chance until someone finds it again. The wreck itself gives clues about the world that produced the machine. It was likely a large merchant vessel traveling from the Greek east toward Italy. Its cargo was expensive and international. There were statues made for wealthy Roman buyers. There were objects from different regions. The ship may have been carrying art and luxury goods during a period when Roman elites were eager to collect Greek culture. The mechanism may have been part of that cargo. Or it may have belonged to a wealthy passenger. We do not know. That uncertainty matters. Was it an expensive scientific instrument? A teaching model? A display piece for a powerful patron? A device used by an astronomer or navigator? There is no label explaining its purpose in plain language. Instead, researchers had to reconstruct its meaning from fragments: gears, shafts, letters, holes, pointers, and the mathematical relationships hidden in its design. It was like trying to reconstruct a clock after it had been smashed, rusted, and left underwater for 2,000 years. The first serious attempts to understand it took decades. In the mid-20th century, science historian Derek de Sola Price studied the fragments using X-rays and photographs. He argued that the device was an ancient astronomical calculator, more complicated than anyone had imagined. At first, his conclusion sounded almost unbelievable. But later investigations would prove that the truth was even more remarkable. The great problem of the Antikythera mechanism was that almost everything important was hidden inside corroded bronze. Looking at the surface was not enough. Researchers needed a way to see into the fragments without destroying them. Modern imaging changed everything. In the early 21st century, an international research project used high-resolution X-ray tomography to examine the mechanism. The scans revealed gear teeth, inscriptions, axles, and internal structures that no one could see from the outside. Imagine using a medical scanner on a patient. Now imagine that the patient is a machine made of corroded bronze, more than 2,000 years old, broken into dozens of pieces. The scans allowed researchers to look layer by layer through the fragments and build a picture of the lost device. They found that the mechanism was not a single dial with a few moving parts. It was a compact system of interlocking gears. At least 30 gear wheels survive or are visible in the fragments, and reconstructions suggest the original device may have had more. The teeth were cut with extraordinary care. Gear ratios were chosen to represent astronomical cycles. One wheel could drive another, which drove another, producing a slow and meaningful change on a dial. This is the essential idea behind the mechanism. The heavens repeat patterns. The moon changes phase. Eclipses return in cycles. The sun moves through the zodiac. Calendars repeat. Ancient astronomers spent centuries measuring these regularities. The Antikythera mechanism turned those mathematical patterns into moving bronze. Turn the handle, and the machine turned numbers into motion. The front of the device probably displayed the sun, moon, zodiac, and calendar cycles. The back contained spiral dials that tracked longer periods of time. One of these represented the Metonic cycle, a period of 19 years that closely matches 235 lunar months. This was not a random number. It was a powerful tool for reconciling lunar months with solar years. Ancient calendars needed to keep festivals, seasons, and civic life roughly in step. The Metonic cycle gave astronomers and calendar makers a way to do that. Another dial represented the Saros cycle, a period of about 18 years and 11 days after which similar eclipses can recur. The mechanism included marks and inscriptions that appeared to identify whether an eclipse would be solar or lunar, and even information about its expected character. Think about what that means. Someone in the ancient world could turn a handle and see an eclipse cycle represented mechanically. Not because the machine predicted the future by supernatural means, but because it encoded observations and mathematics accumulated over generations. The device also modeled the irregular motion of the moon. The moon does not travel across the sky at a perfectly constant speed. Its apparent motion changes because its orbit is not a perfect circle. The mechanism appears to have used a clever gear arrangement, including an offset pin and slot system, to imitate this variation. That detail is one of the most impressive features of all. The builders were not merely repeating a simple calendar. They were trying to represent a subtle astronomical effect with mechanical parts. This was precision engineering in an age when every tooth had to be cut by hand. The Antikythera mechanism was probably housed in a wooden box not much larger than a modern shoebox. It may have had doors or panels covered with explanatory inscriptions. It was small enough to be portable, but complex enough to contain a miniature model of the known cosmos. The front dial was likely the most visually dramatic part. It showed a circular arrangement of the zodiac, the band of constellations through which the sun, moon, and planets appear to move. It also included a calendar scale, probably based on an Egyptian-style year of 365 days, with a possible adjustment system for the extra quarter day. Pointers moved across these scales. One represented the sun, another represented the moon. A small black and white sphere may have shown the changing lunar phase. For an ancient observer, this was more than decoration. The sky governed agriculture, religious festivals, civic calendars, sailing seasons, and the measurement of time itself. Watching the heavens was practical as well as philosophical. The regular movement of the sun and moon helped societies organize life on Earth. The Greek world had a long tradition of mathematical astronomy. Thinkers such as Hipparchus studied the motion of the moon, the timing of eclipses, and the length of the year. Archimedes wrote about astronomical devices and mechanical models. Later writers described instruments that showed the motions of the heavens. The Antikythera mechanism is important because it gives physical evidence that this tradition was not only theoretical. At least some people could turn astronomical knowledge into precision machinery. The identity of its maker is unknown. It is tempting to attach famous names to it. Some have wondered whether it came from Rhodes, an island associated with astronomy and engineering. Others have linked its ideas to the intellectual world of Hipparchus or the mechanical tradition associated with Archimedes. But there is no inscription saying who built it. That is one reason the object remains mysterious. It is a masterpiece without a known inventor. The inscriptions that do survive are precious. They are often called a user's guide, although that phrase may be too modern. They explain parts of the system, name cycles, and describe astronomical phenomena. The text was written in tiny Greek letters, many of them less than a few millimeters high. The builders expected the owner to understand more than the basic motion of a dial. The mechanism seems to have been designed for someone interested in astronomical theory. Yet it may also have been meant to impress. Picture opening the wooden case in a room lit by oil lamps. Bronze pointers move when the handle turns. The moon changes phase. Calendars advance. Eclipse cycles appear. The machine transforms invisible mathematical order into something a person can watch. It would have been an object of knowledge, but also of power. Owning it would announce access to education, wealth, and technical skill. In this sense, the Antikythera mechanism was like a scientific instrument, a calendar, a teaching device, and a work of art all at once. If the front was a face of the sky, the back was a map of time. Two large spiral dials dominated the rear of the mechanism. A spiral is useful because it can show many months or years in a compact space. Instead of one circle, a pointer can travel through several loops, marking a long sequence. The upper back dial represented the metonic cycle. 19 solar years are almost equal to 235 lunar months. This relationship had been known to ancient astronomers and was valuable for calendar making. The dial was divided into 235 months. As the mechanism moved, a pointer would travel through the spiral, showing where a person was in that long cycle. There were also smaller subsidiary dials connected to other calendar cycles. The lower back dial represented the Saros eclipse cycle. Eclipses do not happen at random. They occur when the Sun, Earth, and Moon align in a specific way, but the geometry repeats over long intervals. The Saros cycle was one of the most useful patterns known to ancient eclipse observers. On the Antikythera mechanism, eclipse inscriptions appear in cells around the spiral. These may have indicated the type of eclipse, its timing within the day, and perhaps details about its appearance. The device did not calculate every astronomical event with modern precision. Its purpose was different. It was a model based on the best cycles and theories available to its makers. That distinction is important. When we call it an ancient computer, we do not mean it had electricity, software, or a screen. We mean it performed a kind of calculation through physical relationships. The gears stored mathematical knowledge in their sizes and ratios. When one gear moved another, the machine was carrying out a rule. Modern computers use electronic signals. The Antikythera mechanism used bronze. The lower dial also had a smaller 4-year cycle associated with athletic games. This was a surprising discovery. Alongside eclipse prediction and lunar astronomy was a schedule for major Greek competitions, including the Olympic Games. That detail makes the machine feel human. It was not only concerned with abstract astronomy. It connected the heavens to the social world, festivals, calendars, and public events. The same society that studied the movements of the moon also organized time around religious ceremonies and athletic contests. The mechanism was therefore not simply a device for specialists. It was a bridge between cosmic order and daily life. The phrase, ahead of its time, is useful, but it can be misleading. The Antikythera mechanism was not ahead of its time in the sense that it appeared from nowhere. It was a product of its time, a world of Greek mathematics, Hellenistic science, maritime trade, bronze craftsmanship, and wealthy patrons. What makes it extraordinary is that so little else like it has survived. Ancient writers describe mechanical devices that sound surprisingly sophisticated. Hero of Alexandria wrote about automata, water-powered mechanisms, and theatrical machines. Archimedes was famous for mechanical inventions and for a device that reportedly showed the movements of the sun, moon, and planets. Cicero described a sphere associated with Archimedes that represented celestial motion. These accounts suggest that advanced mechanisms were imaginable and perhaps real in the ancient Mediterranean. But written descriptions are not the same as physical proof. The Antikythera mechanism gives us physical proof. Why did such technology not lead directly to industrial machines, factories, and modern clocks? There are several reasons to be cautious with that question. Invention alone does not transform a society. A machine needs materials, demand, trained workers, investment, institutions, and a reason to be made again and again. The Antikythera mechanism was probably expensive. Bronze was valuable. Skilled labor was expensive. The knowledge needed to design it was rare. It may have been made in a small workshop for elite customers, not as a mass-produced tool for everyday use. Also, ancient societies had different economic systems and different needs. Water clocks, sundials, calendars, and direct observation of the sky were often enough. A sophisticated astronomical machine could be admired without becoming essential. Then history intervened. The Mediterranean world changed repeatedly through war, political upheaval, economic shifts, and the fall of institutions. Technical traditions can survive in texts, but practical workshop knowledge is fragile. A precise gear-cutting method can disappear if the craftspeople who know it are gone. By the medieval period, complex geared astronomical clocks would eventually appear in Europe and the Islamic world. But they emerged many centuries after the Antikythera mechanism. This does not mean the ancient device was forgotten by everyone immediately. Ideas may have traveled, and some mechanical traditions continued. But the direct line from the Antikythera workshop to later clockmakers is unclear. That gap is what makes the machine so haunting. We are looking at an object that proves a level of craftsmanship existed, while leaving us unsure how widespread it was or what happened to the people who made it. No complete Antikythera mechanism exists. Every reconstruction involves interpretation. Researchers begin with what survives: the fragments, the visible gears, the inscriptions, the holes in metal plates, and the relationships revealed by X-rays. Then they propose how missing parts might have connected. Different reconstructions sometimes disagree. A gear may be placed in more than one possible arrangement. A pointer may have served one function or another. The mechanism's treatment of the planets remains one of the most debated areas. Some modern reconstructions include systems for the known planets, Mercury, Venus, Mars, Jupiter, and Saturn. Ancient Greek astronomy had models for their complex wandering motions across the sky. The challenge is fitting those models into the limited space suggested by the surviving fragments. In recent years, researchers have proposed elegant gear systems that could reproduce planetary cycles on the front display. These models are exciting, but they are not the same as finding all the original gears. They are evidence-based hypotheses, not final certainty. That is how good science works. The mystery is not weakened by uncertainty. It becomes more interesting. Each scan, reconstruction, and experiment helps narrow the possibilities. Researchers do not need to pretend they know everything. They can show what the evidence strongly supports, what it suggests, and what remains unknown. This is also why the Antikythera mechanism is more than an ancient curiosity. It is a living research problem. Engineers make working replicas. Historians compare inscriptions. Astronomers test ancient cycles. Archaeologists return to the wreck site. Divers have found additional artifacts, including parts of statues and other objects from the ship's cargo. Every new discovery has the potential to change the picture. The sea may still be holding pieces of the story. There may once have been another mechanism on the ship. There may be missing panels, gears, or tools buried under sediment. Or perhaps the surviving fragments are all that remain of an object whose full complexity will never be known. Either possibility is powerful. The Antikythera mechanism changes the way we imagine the ancient world. It reminds us that people in the past were not less intelligent than people today. They had different resources, different institutions, and different bodies of accumulated knowledge. But they could observe, calculate, invent, and build with extraordinary sophistication. It also warns us against a common mistake, assuming that what has survived is a complete record of what once existed. Wood decays. Leather disappears. Paper burns. Bronze is melted down and reused. Workshops leave few traces. Ships sink. Whole traditions can vanish from the archaeological record. The Antikythera mechanism survived because a shipwreck protected it, even while destroying much of it. It is an accident of preservation. How many other devices were made from bronze and later melted down? How many astronomical instruments were built from wood and lost completely? How many technical manuals disappeared in fires, wars, or abandoned libraries? We cannot know. But the mechanism tells us that absence of evidence is not always evidence of absence. It encourages a more humble view of history. The past is not a simple ladder leading directly to the present. It is a landscape of discoveries, dead ends, forgotten methods, and ideas that returned centuries later in new forms. The machine also has a modern lesson. Technology is not just a collection of objects. It depends on communities of knowledge. A single brilliant device can be made, admired, and then lost if the people, workshops, and institutions around it disappear. That is true now as well. We often assume digital knowledge is permanent. But files become unreadable, systems become obsolete, and archives need care. Knowledge survives only when people decide to preserve it, teach it, and use it. Imagine the Antikythera mechanism as it may once have been. The bronze is bright, not green with corrosion. The wooden case is intact. The inscriptions are sharp. A person opens the cover and turns a small handle. Gears begin to move. A pointer advances through the zodiac. The moon changes phase. A calendar moves onward. Farther inside, hidden wheels convert the turning of a hand into the rhythms of years and eclipses. For a moment, a person in the ancient Mediterranean can hold a model of time in their hands. Then the ship sinks. The machine falls into darkness. Water fills the case. Wood rots. Bronze corrodes. For nearly 2,000 years, no one sees it. When it returns to the surface, it does not give us all its answers. It gives us fragments. But those fragments are enough to challenge our assumptions. They tell us that ancient engineers could make gears dance to the mathematics of the sky. They tell us that science and craftsmanship were deeply connected. They tell us that history has missing chapters. And they leave us with one final question. If this remarkable machine survived by accident, what other inventions have disappeared without leaving a trace? The Antikythera mechanism is not just a relic of lost technology. It is a reminder that the human story is far stranger, more inventive, and more fragile than we usually imagine. If you enjoyed this journey into the hidden record of history, subscribe for more lost inventions, ancient mysteries, and forgotten stories that changed the world.